In this video, I'll discuss about the results and comparison with data from Kim et al. And you will find these two papers in your resources. So in the very first lecture of this section, you will get these two files, this and this file. And also I will attach PDF of this PowerPoint presentation and Y+ calculator. So if you take a look on the Kim et al., you will see that the topic is characteristics of secondary flow induced by 90-degree elbow in turbulent pipe flow. And so same thing, which is that the flow is so when the is greater than the 1.5, the secondary flow consisting of pair of contour rotating what is generated. And so this is all we are doing right now. Okay, so this is the experimental work, and also they have some numerical simulations. Definitely they are using the different velocity and Reynolds numbers, but if you go to the paper by the second main paper is by the Prasan Dutta, so you will find that they are doing the simulations at the given conditions. Okay, and the time step size used in present study is 0.001 with the 1000 time steps. So if you want to go for the transient simulation, then for that case we have to use the time step. So we can calculate this time step very easily, but since this is already given, so we can use this directly in our case. And they have used the hexameshing. Hexameshing is always better in resolving flows. So first thing they are doing is that they are doing the RC by D of 2, and measurement of velocity is performed in Reynolds number of 10 power 10 into 6, 10 power into 10 power 4. So this is 60,000. They have performed the simulation on the mesh of 2.85 million hexahedral elements, and the Y+ is controlled for 30 to 90, but we use a Y+ less than 1. Okay, so the inner diameter of having 0.001 with curvature ratio of R by C by D is equal to 1. So they use a 0.01 of the diameter, and so we did in our case also, and that you can find in the over here. Okay, so you can find these things over here. So diameter is 0.01, and the RE Reynolds number based on diameter is a 60,000, RC by D is 2. And so this is the case we are comparing, and we will compare the data at this line, okay, at the end of the band. Okay, so let's create the line over here where the x is equal to 0. So I will use the y from how much value? So let me calculate. So basically we have the pipes like going this way. Okay, this is the start of the band, this is the end of the band. Okay, here x is equal to 0, this is very confirmed, and origin system is over here. Okay, so from this point, this x, y, z origin to this is like this. Okay, so up to center point, the distance is 0.02. So it means that if I take the x is equal to 0, so the y should be varying. Now if you take a look here, if you go on this side, this is going to be equal to diameter is 0.01. So if we divide by 2, this is 0.005. So this location would be 0.02 minus 0.005, and this location would be in the y direction. This would be 0.02 plus 0.005. This is equal to, let me calculate, 0.02 minus 0.005 is a 0.015, and here this is going to be 0.025. Okay, so let's create line at this location. And you can also do this thing in CFD post. So let's try this thing in the CFD post. Okay. All right. So we have this geometry in the CFD post. And if you take a look here, so we can make this band as transparent. So okay, and similarly for the wall number 2. Okay, so I'm going to make a line over here. So location and the line. This line will have the z is equal to 0 and x is equal to 0. Okay, and the y will be varying from 0.01 to 0.025. This line. Okay, now again this is on the symmetry plane. So this is symmetry plane is this one. So there's no doubt that this line will be here or here. This is on the symmetry plane. Symmetry plane is passing through the mid of geometry. So this line should be over here. Okay, now if we plot the chart and data series, so you can say it's a velocity profile, and the location is a line number 1. And on the x-axis, let's say we go with the y location, and the y-axis we are going with the velocity. So now you can change the number of the points or samples into the line. So let's say we make it 80. Okay, or maybe more. Okay, and if you go back to the chart, you can see that okay, so you can use a solid line, and for the color you can do it manually. So let's say we choose a black color, and we choose some symbols also. So this is how this graph will look like. So if you compare here, this is something like this. Okay. Okay, so this plane, let's say now let me show you this where this plane is being discussed. So this plane is over here. Okay, so this is alpha 0, this is alpha is equal to 90 degrees, and here the y is varying from minus 0.005 to plus 0.005. And why? Because I made this point at the y is equal to 0. That's why we make the line at this location in this way. But because we maintain the origin on this location, that's why we have to calculate the y in this way. So we have the data for this case. So now let's compare data in the Excel. So Excel would be the better software. Okay, so I'm going to output this whole thing from here. Okay, so you can export the file from here, and so put the name as velocity profile at 90 degrees, and let's open the Excel. And now look for the file. So the file is somewhere inside. It should be here. Okay, it should be here, 90 degrees bend. and inside these files, and it is inside the user files, it's a velocity profile. So you can directly open from here as well. Okay, so if you plot this data, you can get the graph in this way. Okay, the first thing is that the graph is basically, if you take a look on the graph, this graph is made on the normalized y distance that is varying from plus 0.5 and minus 0.5. So how we can get this thing? We can get this thing by dividing with its radius, its diameter. Okay, so in this case, this is going to be the 0.015 divided by 0.01. This is 1.5, and 0.025 divided by 0.01, this is equal to 2.5. So if I subtract 2 from these both values, I get the minus 0.5 and plus 0.5. Okay, so this is what I'm going to do in the Excel right now. So the first thing is that I'm going to divide the location by the 0.1. So 0.01, and like this. Okay, and right click here and simply format. So general number should be like this. Okay. The next thing is that I'm going to subtract the 2 from these values. Okay, and next thing is that this is about our location. This is let's say it's x. This is the x-axis, and on the y-axis we have the velocity. So I will divide this velocity by the incoming velocity, that is 6 meters per second. So we have to normalize the velocity as well. So dividing by 6. Okay, and one more thing is that this graph is distance is along the x-axis and the velocity is along y-axis. So I'm going to provide the same thing here as well. First right click and format cells and numbers. So 1 minute. Let's make them separately. So because we need more spaces, we need more zeros or decimal places in the case of the velocity. So I will be putting, let's say, 4 decimal places. Okay. So now plot this velocity also. So insert and chart. Okay, now this velocity is varying from here and there. So we have plotted this data. The next thing is that we have to compare data with Kim et al. So we need to have the data from the Kim et al. And I told you that we have these 2 papers. And if you take a look on this paper, you will see this graph. Okay, so I'm going to use the snapshot option and take a snapshot for this picture number B. Okay, and open Paint, a new file, and paste your picture over here. Okay, like this. And you can save this picture. Let's say this is the Kim data. And next thing is that we have to open any app or any software that can convert our graph into numbers. Okay. Okay, so here is an app that is online and it's free to use. That is a web plot digitizer. Click over here and you have to launch for the desktop version. You can also download for desktop or Android or Apple, but you can also use on the desktop. So click on launch now. Okay, and then from the file menu, load images, choose file, and this file is a Kim data. So first thing is that we have to align axis. So axis is from, you can see this is from 0.4, 0.3, 0.2. So this is minus 0.5 to plus 0.5. Okay. So proceed. This is, now you have to look for the precise point. So maybe there is you cannot do it by mouse, but try to be as precise as you can. Okay. And this will also introduce maybe some errors in getting the data from the graph. So it's okay. Okay, so we have taken the 2 points for x, and then we have to take the point for y-axis. Okay, and then at 1.2. Okay, so now you have to write down the points for x-axis minus 0.5 and plus 0.5, and for y-axis the points are 0 and 1.2. Click on OK. And now you have to find the data in these hollow squares. So hollow squares are here, so you can zoom it. So first one is at the 0, first, second, third, fourth, fifth. So just continue with all these boxes. So take all these points. Okay, so now you have to click on the view data, and from here you have to copy these all points, and then go to the Excel sheet, and you have to paste somewhere, so you can paste over here. Okay, now you have to convert this data into columns. So text to columns, and space, finish. Okay, so this is the, let's say now this is the Excel location. This is the, let's say this is the Excel distance. Okay, whatever it is. And this is the normalized velocity. And this is from CFD. And this one is, again, it's the same thing as the axial distance. and this is normalized velocity, and this is from the Kim et al. Okay, so you can insert the different things here, like you can put the borders, make them bold so that you can have some good graphs here, some good data points in the Excel. So this is how you format. So you know about this thing, I think, very well. So I will just do it quickly. Okay, this is about the Kim et al. So I'm going to remove the commas. Okay, now we have the data from Kim et al. At the Reynolds number is equal to 60,000 and curvature ratio of 2. So in the same graph, select data and edit the title of this data to CFD. Okay, and the mesh size is around 0.8 million. Okay, and then add a second series, and the name would be the Kim et al. Okay, so again we have to in the x-axis the distance, and in the y-axis the normal velocity, normalized velocity divided by the incoming velocity. So if you take a look on the graph, you can see some differences. Okay, so if you take a look on the graph, so let me make it more meaningful so that you can visualize that what we are talking here. So the Kim et al. Data is in the orange color, and the data from the CFD is in the blue color. So you can see a lot of difference here. Okay, so this difference because of the mesh quality. This is because of the mesh quality. Okay, so in this way, basically, we made the validation of the data from the Kim et al. And the data from the CFD. So now if you take a look on the file which is provided with the course, that file has a better mesh quality. And one more thing is that